Swayam Prabha. Digital India. Educated India.
Hello everyone, today I will start module 8, the surface modification and characterization 2. So, in this module we will first discuss the surface characterization part, then next we will see a chemical method to modify the surface, particularly formation of self assembled monolayers, then we will see the effect of self assembled monolayers on the biointerfacial interactions. So, we will quickly summarize the last module. In the last module, we discussed various surface modification, what is surface modification, what are the objective to tune the different surface properties. Then we discuss what are different surface modification routes, particularly the physical methods, biological methods and the chemical methods. And in the last lecture, we just saw the application of one physical method, particularly RF sputtering and the laser cladding. So, we discussed the coating of calcium phosphate on titanium surface using the physical method and its effect on its physical, chemical and biological properties. So, today we will start with the characterization of the surfaces. So, broadly these characterization techniques are classified into microscopic technique and these spectroscopic methods. So, in the microscopic techniques means we are going to use a microscopy and that microscopy may be your optical microscopy, electron microscopy, scanning probe microscopy, field emission or field ion microscopy and low energy electron diffraction microscopy, or this is also sometimes called the X-ray microscopy. X-ray microscopy. So, basically the whole objective of microscopy is to view the sample, the morphology or the object in the range which we cannot see with the naked eyes, and typical range varies between the millimeter to nanometer. Now, depending on the source of light, in case of optical we are using the visual light, electron microscopy we are using the electron as a source, scanning probe basically this is a piezoelectric method. So, where we are applying the piezoelectric cantilever to scan the surface and in turn it creates the surface image or surface morphology. So, depending on the different sources of light or different energy sources, this microscopic is characterized like this, and as we are having different energy sources, different light sources, so the resolution also varies. So, particularly for the optical microscope, resolution is about 500 nanometer. Resolution means it can resolve the distance between two particles or the different two structures. So, resolution of optical microscopy is 500 nanometer, for electron microscopy it is 1 nanometer or even it is less than 1 nanometer. For SPM it is less than 1 nanometer up to the atomic level. This ion field emission or field ion is 3 to 5 nanometer, and the X-ray microscopy it is 0.01 to 10 nanometer. So, these are the resolution of different microscopic techniques. So, in case of optical microscopy, this is also known as the light microscope. So, how we calculate the resolving power is defined as 0.61 lambda. Lambda is the wavelength of incident light divided by the numerical aperture, and numerical aperture is defined as n into sin alpha, where n is the refractive index of medium and alpha is the half angle subtended. So, in this way we calculate the what is the resolving power. So, basically if you are using this light source, means we are using the visible light, and that is why the resolution will be very much proportional to the lambda of the incident light, particularly for light microscope we are using the visible light. Apart from this light microscope, recently we also use the confocal microscope. So, which it has the ability to visualize the objects in a 3 dimensions, and particularly it is very useful for the biomacromolecules or biological samples. Let us say for the cells or the membrane. Now, next after optical, this is the electron microscopy. In the electron microscopy, these are the 2 common, one is the scanning electron microscopy SEM, and second is the transmission electron microscopy TEM. So, in case of SEM, we are using the electron beam, that is a energy source. As in case of optical microscopy, you use the visible light, but here you are using the electron beam. Now, this electron beam is directed toward the surface, and now this highly concentrated electron beam is generated from the electron gun, and this beam strikes the your surface and interacts with the surface. Now, when this electron beam interact with the surface, there will be the electron emission. So, that will be the X-ray emission, it will be the back scattered or primary electron, it may be the secondary electron, it may be the auger electrons. Now, this SEM make use of these electron emissions, it may be primary, back scattered or secondary, but mostly we use the secondary electron to make the images or to analyze the samples. So, these images has a wide range in the contrast and great depth of focus. It means it enables to scan even the surface with large roughness, which cannot be analyzed using the atomic force microscopy, or you can say the scanning tunneling microscopy. So, because of these features, even if you are having the roughness in the range of let us say micrometer rough surface, we can analyze using the SEM, but only your substrate or your sample should be stable if it is exposed to the electron beam, and also it should be conductive. So, in many times for SEM analysis, this is your sample, let us say this is your sample. So, we have to sometime coat some conductive film like a silver or gold. Coating is also done before the SEM analysis, and many times along with the SEM we have the energy dispersive X-ray analysis, that is called the EDX, particularly for the elemental analysis. So, when the electron beam with the energy in the range of 10 to 20 kilo electron volt strike the sample surface, then as I told, the energy of the emitted X-ray, it depends on the property of the material, or you can say the composition of the material, and this composition or amount of the material are estimated depending on the energy of the emitted X-ray. So, now indirectly we are using a high energy beam, and then we are measuring the energy of emitted X-ray, which depends on the composition or the amount of element present on the top of the surface. So, in this way mostly this SEM is coupled with the EDX. SEM is coupled with the EDX. So, it is giving two information, morphology and elemental analysis. So, after the SEM, next is the transmission electron microscopy. So, here as the name suggests, transmission means the electron beam is transmitted through the samples to form an image. So, basically apart from the surface, here the electrons, or you can say the beam of electron is transmitted, and if it is transmitting, there will be diffraction, and the diffraction of electron beam, it occurs after interacting with the sample, and this diffraction intensity, it varies depending on the property of the sample. So, what are those properties? The property is the orientation of plane with respect to the electron beam. So, after that, if you block the deflected electron and only allow the unscattered electron to go through, then we obtain a contrast image, and that is known as the light field image. And if you only take the deflected electrons to form the image, that is known as the dark field image. So, we have both the light field image as well as the dark field image. So, dark field image is coming from the deflected electron, and light field image is coming from the unscattered electrons. So, as electron need to transmit through the samples, so this technique is limited to the nanoparticles or the thin film. So, this is very much limited to the nanoparticles and the thin films. So, next microscopy is the scanning probe microscopy. So, in this SPM, two methods are most commonly used, that is the scanning tunneling microscopy STM and atomic force microscopy AFM. So, in case of STM, we measure the exponential decay in the tunneling current between metal tip and conducting surface. So, basically here we require a conducting surface, and as it is a conducting surface, so we are also using a metal tip, and what we are measuring is exponential decaying of tunneling current, right. So, we are measuring the exponential decaying of tunneling current between metal tip and your conducting surface. Now, here we go for the AFM. So, here we are using the deflection. Now, we are measuring the deflection, this is your surface and this is your tip. So, between the tip and surface there will be different intermolecular interactions, and these interactions it may be the capillary, electrostatic, van der Waals or friction forces, and because of these interactions there will be deflection in cantilevers and this deflection is measured. So, here we are measuring the deflection, and here in case of STM we are measuring the decaying tunneling current. So, in case of AFM this is used for the morphology or the topography, and apart from the topography it also gives information, or it can be the post processes to particularly to analyze the roughness parameters. And apart from the roughness parameter, it also measures the adhesion force. Now, how it works? It uses a piezoelectric cantilever and a tip is attached to it, which scans the surface. Now, during the scanning of the surface, we can scan the surface either in contact mode or in a non-contact. Sometimes it is also called the tapping. In the tapping mode, so as the tip approaches to surface or surface approaches to tip, basically surface is fixed, tip approaches to the surface. So, a small deflection is observed because the attractive interaction between the tip and surface, but when it goes further closer, then there will be again a repulsive forces. Because of this attractive and repulsive forces there will be deflection, and cantilever's deflection away from or its movements towards the surface is detected using a laser beam. So, basically we are monitoring the deflection through a laser beam, and this deflection is recorded by a photodiode, and that is converted to generate the image. So, if you remember the I think module 1 when we discuss what should be the minimum force one can measure using the atomic force microscopy, or particularly using this van der Waals forces. So, it measures in the range of piconewton, 10 to the power minus 13 to 10 to the power minus 16 Newton. Now, after the microscopy we will discuss the spectroscopic techniques. So, in spectroscopy again the surface is irradiated with a probe beam. It may include the photons, it may include the electron, it may include the ions or combinations like photons and electrons. So, accordingly the spectroscopy names are also classified like electron microscopy, photoelectron microscopy, infrared spectroscopy or ion scattering spectroscopy. So, basically these spectroscopy techniques are mostly used to determine the functional groups, to determine what are the different chemical bonds or what is the interaction between, you can say, two molecules. So, because of the interaction there will be make and break of some bonds, and these particularly functional groups or bonds are detected using these spectroscopy techniques. So, first we will discuss the photoelectron spectroscopy. It is also known as the X-ray photoelectron spectroscopy. It means we are also using photons and electrons both together So, this is very much surface sensitive techniques for analyzing the surface chemistry, but again the thickness should be in the range of 1 to 10 nanometer. It provides Hamilton analysis, chemical and electrochemical state of elements, also the density of elements. So, these are the XPS is very important technique, particularly for the precisely analyze these elements, chemical functional groups, different bonds, also the density of elements. So, in case of XPS, a continuous beam of monochromatic X-ray is irradiated as sample, and because of this electrons are emitted from the surface, and this emission of electron, it depends again on the what happens at the surface, and which ultimately depends what is the property or what is the composition of the surface. So, basically we measure their kinetic energies of those electrons. So, when we are measuring the kinetic energy and the binding energy, we analyze the elemental and as well as what are their chemical state. So, basically if we just see the energy of binding or binding energy is the difference between the energy of X-ray used. So, this is the energy of photon minus E kinetic energy of the emitted electrons minus, or you can say we are summing them, is the minimum energy required to eject electrons from the atom. So, it says the difference between the energy of the X-ray used minus the kinetic energy and the work required to eject an electrons from the atom. So, this difference is coming because of this interaction between the electron and surface, and that energy is referred as the binding energy. So, once we are able to measure the total energy of the electrons ejected, it means it can be correlated with the composition of the material or the particular sample. Now, the number and intensity of the peak from an element reflect the characteristic energy. As I told, this interaction between the surface and that energy source, the X-ray, and this intensity and the number of peaks are compared with the standard database to explore the composition. So, basically we will get the XPS spectra, and this spectra is compared with the standard database. So, in many times in the standard database we observe a chemical shift, and this particularly chemical shift refers the change in the binding energy of a core electron of an element due to alteration in its chemical bonding. It means a atom may have different binding energy, it depends what types of chemical bonds it is having in a particular compound or a particular molecules. So, because of this its chemical binding, or you can say because of alteration in its environment, we also observe the chemical shift. So, it gives what are different elements are present, what are the different functional group or different bondings are available in that particular sample or particular material. So, after the XPS, we will also use the XRD. So, basically this is commonly used to characterize the crystalline materials. So, here we basically analyze the crystal structure and unit cell dimensions of the materials, So, in this method a monochromatic X-ray beam, this monochromatic X-ray beam is coming on the sample and its diffraction is recorded here, and this diffraction satisfies the Bragg's law, which says n lambda is equal to 2d sin theta. So, here n is a positive integer, lambda is the wavelength of the incident wave, d is the interplanar spacing of the sample, and theta is the angle of incidence of that light source. So, typically for X-ray the source is copper K alpha and the wavelength is about 1.54 angstrom. So, here what we are seeing is we are having a X-ray source and we are having a detector to monitor record its diffraction. So, diffraction of X-ray from all possible directions in the range of the 2 theta value is collected, and again this diffractogram, or you can say again the spectra of the sample is compared with a database to analyze what is its particular phase and what is its crystal structure. So, we analyze what is the unit cell dimension, what is its crystal structure and what is its phase also. So, as I told, from the spectra we will have the peak position, we will have the intensity, we will have some shape of that spectra. Peak position gives what is particular phase, like if you are comparing this hydroxyapatite. So, whether it is hydroxyapatite or it is a tricalcium phosphate, beta tricalcium phosphate, then it also gives the HKL value, unit cell parameters and pattern indexing. From the intensity we analyze the which phase is present in the more amount, phase abundance. Also it gives some information about the texture analysis and the reaction kinetics, and the shape of curve gives the average crystal size, its line profile analysis and the crystal growth kinetics. So, these information from the peak position, intensity and shape are analyzed. Particularly this phase identification, the unit cell parameters and the crystalline size are most commonly used. So, to determine the average crystal size, we use the Scherrer equation, which says d equal to k lambda upon beta cos theta. So, where k is a shape factor, its value is 0.94, lambda is the wavelength of incident X-ray, and what is the lambda? We discussed in the last slide, it was 1.54 angstrom, and beta is the intensity of line broadening at half maximum intensity. So, basically this is the intensity of the peak and the theta is the Bragg angle. So, basically these informations are already provided during the XRD analysis, and from these informations we can calculate the average crystal size. So, next is the we will discuss the FTIR quickly. So, FTIR as we have already discussed, here we are using the infrared light source. So, it is called the infrared spectroscopy, and why it is called Fourier transform is this whatever infrared light is processed after the sample, it is either absorbed or it is either transmitted, that is again processed using a Fourier transform, to get the particular spectra, or you can say the FTIR spectra. So, basically it works based on the bond vibrations. Why it is happening? Because of the your material is absorbing the infrared radiation in a particular wavelength region. So, depending on the wavelength, this IR is classified as a near IR, mid IR and far IR. So, near IR means wavelength is 1 to 2.5 micrometer, mid IR is 2.5 to 25 micrometer and far IR is 50 to 1000 micrometer. So, different functional group will get activated at a particular wavelength, or this is the wave number. So, most commonly you go for the mid IR region 400 to 4000 centimeter inwards. So, infrared spectrum of either absorption or the transmission or emission is used to analyze the atomic or molecular vibrations, and depending on this a particular wavelength we decide which particular type of functional group is present, like it is a C double bond O or bond C or C bond N. So, depending on that it may be C double bond O, C bond C, C bond N or N bond H. So, depending on the particular bond, so all will have the different, or you can say they will absorb the infrared radiation at a particular wavelength, and that particular wavelength will get the particular spectra or particular peak. So, from that FTIR spectra we analyze what are the different functional groups are present in a particular sample. So, apart from the FTIR spectra we also use the scattering. So, that is the ion scattering, or you can say the Raman spectroscopy. So, it is also called the inelastic scattering or Raman scattering. So, it uses the light source is the monochromatic laser. It analyze again the rotational, vibrational and other mode of molecule in a system. So, it is very much similar to the rotational, vibration and any other mode, it is very much similar to the FTIR. So, whatever information we are getting from FTIR, we used to get the similar information using the Raman spectroscopy. So, here as we are using the laser, so laser beam illuminate the samples, and once the radiation is coming from the laser beam, after the sample it is collected with the lens and it passed through a collimator, it means which narrows it. So, your laser beam is coming to sample and radiation from the laser heat spot is collected by the lens, and then it is narrowed down through a collimator. Now, if you expose a molecule with the laser, so molecule gets excited to higher energy level and it is relaxed into a vibrational excited state. Because of this scattering, and typically the interaction between the photons and the laser light results in a shift in the energy, and this shift in energy provide the information about the vibrational mode. It means depending on a particular functional group, we will observe a different shift in the energy. So, as I told, different rotational, vibrational of the molecules, or you can say the different functional groups as we analyze using the FTIR, the similar information we get from the Raman spectroscopy. So, here I conclude. So, today we discuss particularly the characterization of the surfaces. So, we start with two methods, that is microscopic methods and the spectroscopic method. In microscopic methods, the resolution varies from 500 nanometer to 0.01 nanometer, starting from your light microscope, optical to electron microscope, to then scanning tunneling microscope, STM, then SPM, FM and so on, and X-ray microscopy. Then we quickly discussed one by one, starting from this optical microscope. Then we briefly discuss about the electron microscope. Two common methods are the scanning electron microscope and transmission electron microscope. The SEM is used basically for the morphology, and it, but only is your material or sample should be stable when it is exposed to the electron beam. So, we get the morphology even for the rough surface. Now, in case of TEM, as electron need to be transmitted, so it is applicable basically for the thin samples. Then after the microscopy, then we discuss the various spectroscopic technique. So, again in spectroscopic techniques, it depends what is your source or what is the light source. It is the photon or it is the electron, it is the infrared or it is the ion. So, if you are using the photon and electron, so we call the photoelectron spectroscopy. So, we discussed the how XPS works. Then if you are using the infrared, we call it the infrared spectroscopy, and also we discuss the Raman scattering, or you can say the Raman spectroscopy. Thank you.